Okay, everybody, so I promise this will be the last video on parametric equations. I made part 1, then part 2, then part 3, and now part 4. I promise there won't be another part. Anyway, but this is the slide that we started with. So if you're needing to catch up a little bit, go look at the other videos. And I wanted to start with an application of parametric equations being projectile motion. Okay. All right. So just consider a scenario real quick, and then we'll get into the math. So suppose that you throw something through the air. Okay. Then it will take this path right here, illustrated in green, and that's called the path of the projectile. The projectile being something that's just thrown or launched forward. Some details about something like that is that if it's thrown forwards, then it will have like an upward angle of theta, let's say, that it's initially launched at. Okay, so if I was going to launch something, if this pencil was the barrel of a gun or something like that, that would be the initial angle that it's launched at. And then it travels through this predictable arc through the air after that. So that's what theta is. That's the launch angle. It has to also be launched at some initial speed. We'll say v0 feet per second, okay? And we can argue about units. We'd say, why not meters per second? Okay, you could do meters per second, but it won't match my equations. We'll have to change some of the details about them. So let's say that v0 will be in feet per second, all right? And we will launch the projectile a certain number of feet above the ground. And then those are the details. Like we need to know v0, the initial speed that it's launched at. We need to know the launch angle. We need to know the height above the ground that it's launched at. And then it will travel through the air. And we want parametric equations that track its flying, its location through space as a function of time, right? Now that's like my very first example that I gave you with parametric equations. I said you could think of it like that it's motion, and x and y is a place in two-dimensional space, and t is time. And if something's in motion, that every time it is at a certain place. And that's what these equations do for us, all right? Okay, so you can think about it like that. Now, for a projectile, given that you know its initial speed and its launch angle and the height above the ground that it's launched at in feet, all right? Then here are the parametric equations for it. At any time, these will tell you its position in space, x and y. All right? Okay, so now that's the introduction to the scenario. We'll just take the equations for granted. I won't derive them. You can do that in physics class. So we'll do this example, though, just to try things out. So suppose a rock is thrown at some initial angle of 27 degrees to the horizontal, and its initial speed is 101 feet per second. Let's see, that's pretty fast for a rock. Can you throw a rock that fast? Maybe you can. 100 feet per second. Yeah, I'm sure that somebody can. Anyway, from a height of 3 feet above the ground, how far forward will it land? Okay. Well, so you got the picture on the other page, but let me label something about what I'm going to find. Okay. So I'm going to think of it like this. Let's see. So I don't know, like it's launched or thrown from a height of 3 feet. It's obviously not to scale. All right. Rises up, falls back down. And we're looking for this point. Like, where is this point right here? Okay. How many feet is it from here to there? All right. Okay. So that's my goal with this one. Now, what are our equations? What are we working with? So I've got these, and I'm just going to copy these down, given that I have my v0, my theta, and my h, and so on, okay? And so here are the equations that will govern that path right there that you see. It will be, so x is equal to t, v0, 101, cosine 27 degrees. Okay. And then y is equal to h, which is 3, right? It's thrown forward from an initial height of 3 feet above the ground, so 3 plus t times v naught sine theta, okay, minus 16t squared. So those are the equations that we're dealing with for that, okay? Now imagine, like, these are the parametric equations for this arc. At any time, these tell me position x and y. And I want to know where this spot is. Well, one thing I know about that spot is it's on the ground. Okay, so we're thinking of this like it's the ground. And this initial height that the thing is projected from or thrown from is 3 feet. Okay, so that would mean that I want to find how long is it going to take to hit the ground first. Okay, so when will it hit the ground? All right, when will that hit the ground? Well, okay, so one thing I know about that, according to these equations, is the y-coordinate of its location will be 0 at the moment it hits the ground. Okay, so as far as the when, I can start by saying, well, y is 0. And if I do that, then I get this equation. 0 equals, let's do a little rearranging. Negative 16 t squared plus t times 101 sine 27 plus 3, right? And if you could solve this for t, that would be the when. That would be when it hits the ground. And then if you could take that time, when it hits the ground, and put it there, it would be where it hits the ground. Because remember, t is when, and x and y are the wheres. All right? Okay, but how do you solve this for t? Well, that is a quadratic equation. So let's write down the quadratic formula for it. All right, so there's the quadratic formula for this. That'll solve t for us. Oh my goodness. I'm so used to solving quadratics in x. That will give us t, right? All right, t. And then we're going to have to do some math on that one. So let's do the math. Okay, so if we do a little math, then we get this, and I've done some rounding with those numbers. So at this point, it's only approximate if I go a little bit further, but we could perhaps store those on our calculator if we needed more accuracy. And as far as my solution to this, it's going to be the negative 45.8 minus root 22.94 over negative 32. Because that would be a negative over a negative, and that's going to take me out there. All right, it's going to give me a positive value for t. So let's do the math on that, and I'll find t is approximately 2.93 seconds, okay? Because my time units are seconds. So that's the when it will hit the ground. As far as where it will hit the ground, meaning how far out that way, that will be the x coordinate of its location at the moment it hits the ground, okay? So if I take that number right there, and I do x is 101 cosine of 27 degrees times that number, okay? Right, because there's my equation, 101 cosine 27 degrees times t. I know the t, so I'll take that times 101 times cosine 27. And then I get 263.5 feet, okay? So x will be about 263.5 feet. Feet are our units for distance, okay? All right, so first I find the when, and then I can find horizontally the where, as far as where it hits the ground. All right, I like putting my answer back in, where I started. I say, see that point right there? Let's throw it forward, travels through this arc, hits the ground. Okay, so that's going to be 263.5 feet. That's how many feet forward it is to right there. Okay. So, all right, there's one basic, fairly basic example with parametric equations. Now, something I want to follow this with was the fact that projectile motion is parabolic, okay? So, in other words, like this arc that rock would, travel through before it hit the ground, rise up a little bit, fall back down, that is a parabola. It's parabolic, okay? So, I wanted to first make that statement and then see if I could show you why I think that is, okay? So let's say that I tell you that right there, meaning our parametric equations for projectile motion, has this path, all right? You remember what the path is? That's just the y and x equation that the thing travels through, okay? That the parametric equations are if you graph them. So can you find what h is supposed to be? Can you find what v naught is supposed to be? And can you find what theta is supposed to be? All right? Okay, now, so first of all, if I'm going to make this match up with that, like first, this problem, I mean, as I've given it to you, it just takes it for granted. This is just a statement that if you plotted out that path right there, it would be this parabola, okay? So how are we going to reconcile these? Can we, let's say we'll take this approach. How would we ordinarily get the path of some parametric equations? We would say, well, we could find the path by eliminating t. That's how we've done it before, and that's still how we can do it here. So I can eliminate t fairly easily. I can say divide this by v naught cosine theta. Oh, whoops. Yeah, x over v naught cosine theta. And then, given that that's how I can solve for t, I can put it into this. Okay? So take that, sub into that second one, and I'll get y is equal to h plus x over v naught cosine theta, okay, times v naught sine theta, okay, minus 16 times t squared. All right, so there's me taking that, solving it for t, and then substituting that t in the other equation. And now I've got something that's kind of a mess, but it's just in terms of x and y. So t has been eliminated, and that's the path, okay? All right, but let's do a little cleaning up out of this. Let's say, all right, well, let's see. I'm going to put this term first, okay? So, like v naught cosine theta, that would be a constant, right? And x is the variable in the path. It's a path in x and y. So I'm going to do negative 16 over v naught cosine theta squared. Okay? Then for the second term, I notice the v naughts are going to cancel, and I get sine over cosine. So I'll say plus, what's sine over cosine? Is there any identity for that? Tangent. So tangent theta x. Okay. All right. And then h. And I just wanted to put it in typical form that we give quadratics or parabolas. ax squared plus bx plus c. So here we go. So so negative 16. Oh, whoops. I forgot the x squared. Negative 16 over v naught cosine theta squared. That's all a constant times x squared plus tangent theta, sine over cosine with b naught canceling, x plus h. All right. So now this is the thing right here that, links up pretty nicely with that. And now you can see why our projectile motion parametric equations have a parabolic path. There's the path. It's ax squared plus bx plus c. It's the form of a parabola, okay? All right, well, what is all this stuff then? What's h and b naught and theta? So, well, first of all, just by comparison, that there's a coefficient term of x squared. and then a coefficient term of x, and then h. We can tell that h is equal to 6. Okay, so then what can we find next? I guess again by comparison, given that the coefficient of x is tangent theta, but here it needs to be 1, then I can find theta. Okay, so let's say like just by linking these together, by seeing that, well, they have to be the same thing. All right, then I can say, well, okay, h is 6, tangent theta is 1. Okay, see, tangent theta has got to, what's that coefficient right here? 1. So what's that make theta? Theta is 45 degrees. Okay, because tangent theta is 1. All right, so 45 degrees for theta. Okay, now let's V naught. Oh, we'll go to this one. I've got the theta. I solve for V naught. That's got to be this. Okay, so my last one. So here's my first, second, and then third thing I'm linking between these is that negative 16. V naught, which I don't know yet, cosine of 45 degrees, all squared, has got to be this coefficient right there. Okay, so that's going to be negative 0.008. All right, well, there's only one thing to solve for right there, and that's V naught. So I'll do a little multiplying. And say I take that as cosine of 45 degrees, which I'll have to square. I can put it over here like this. And that will be a half. Okay, what's cosine of 45 degrees? Well, it's 1 over root 2. Okay, what if you square it? It's 1 over 2. And say you multiply that number over there. It's 1 over 2. So I'll get like so. And then I'll multiply, divide, and then take the square root. So I'll get V naught is equal to root 16 over 0.004. All right. We're doing a little math on that, and dividing, and taking the square root. All right, let's see what that number is. So root 16 divided by 0.004. All right, that's what I got. So that turns out to be 63.2 or so. What was the number I get? 63.245 or so on. So let's say V naught about 63.25. You know, you'll just have to follow the instructions for rounding that are given to you, but that's what I get. Okay. All right. So let's quick summary of this one before I let it go. There's our parametric equations for projectile motion. It happens that projectile motion is parabolic. Let's say that some particular projectile follows this parabolic path. Can you figure out what that initial height is, initial velocity, and launch angle? All right. Well, so first I got to have a way to link these together. So I found the path. I eliminated t out of that. I solve for t. I substitute in the other one. I get this. This is definitely a parabola. It's quadratic. It's ax squared plus bx plus c. It links up with that. And one term at a time, I can tell you what everything needs to be. Okay? All right, so let's say the question from the beginning was to find those three things, those three aspects, and I got them. Okay, so we did projectile motion. We did two problems on that. One more that I think might be kind of a hard problem for this topic, so I'm saving it for last. And it's, say like it could be, this could be like any problem that we did so far, except for it being a little bit harder, where like I give you some parametric equations and I say, can you sketch the graph of it? Can you tell me which direction along that path you would go as the parameter advances? Okay, t is 0, t is 1, t is 2. You're going that way. Can you do that? Can you give the equation for the path? and so on. So I want to do something like that. I just think that this one is a little bit harder. So let's see. About this, say first part I ask you is, can you find the path of this particular set of parametric equations? Then it involves trigonometry, okay? And I know that we did some problems already like that, like this one. If you were to find the path of this one, we would make use of this identity, sine squared plus cosine squared is 1, okay? So, with this one, there's going to be another identity, all right? That's just going to be the nature of it. So, let's see. There is an identity between secant and tangent, all right? And you can get it from the Pythagorean identity, it turns out. So here's what I mean. Let's see. So remember this identity. So what was it? Sine squared theta plus cosine squared theta is equal to 1. Now, say we know that one. That's how I'm going to get the identity between secant and tangent. Unless you remember it. If you remember it, great. But okay, so what if I took this one and I divided every term on both sides by cosine squared? Okay. What's sine squared over cosine squared? That's tangent squared. What's cosine squared divided by cosine squared? That's 1. What's 1 divided by cosine squared? That's secant squared. Okay, so there's an identity that relates tangent and secant. It's not quite in the form that I need it to be for this one, though. So I'll do this. I'll move the secant over, or let's scratch that. I'll move the tangent over, and I'll get 1 is equal to secant squared theta minus tangent squared theta. Okay, so here's the identity I think we can use for this one. I'll use it in a similar way to how I've done sine and cosine with some other problems. Okay. All right. So here goes. Let's work on this. See if we can find the path. That will involve eliminating the parameter. Okay. How can we eliminate the parameter? How can we eliminate theta? So think of it like this. So say I say that secant theta is x over 8. All right, that's easy to get from the first one. And say I tell you that tangent theta is y over 7. And then I know there's an identity between secant squared and tangent squared. So suppose I square both sides of this one, and I square both sides of this one. I would get secant squared is x squared over 64, and tangent squared is y squared over 49. But secant squared minus tangent squared is 1. So it would turn into this. Here's my path. Secant squared, x squared over 64, minus tangent squared, which is y squared over 49, is 1. Okay, so there's my path. What is that path? That is a hyperbola. And I know if you made it to calculus 2, you know what somewhere somebody taught you what a hyperbola was. Okay, it's hard to remember every detail of all the conic sections, but I'll tell you real quick review. Hyperbola has at least one oriented this way, has that equation. This point and this point are plus and minus root of that number. All right, a and negative a, and it forms to these lines formed by y is b over a and y is negative b over a. All right, so that's the very much the crash course on what a hyperbola is. All right, so yeah, if you were to plot that out, it would be a hyperbola. Where's that point going to be? Where's this point going to be? 8 and 0 and negative 8 and 0. All right, now from here, if I was going to sketch the graph, if I'm going to do this on paper with pencil without relying on anything or anybody to do it for me, then I'm going to have to do some math. And I think that probably if you're in calculus 2, you need to learn to do some math also. I guess it's fine at some point to rely on graphing calculators and computers and so on to do stuff for you. But if you have no clue what it's giving you or how it got it, I don't really see what good that is, okay? So I'm going to show you in quite a bit of detail how you would sketch the graph, all right? So here it is. There's the graph of my hyperbola. What I notice about this is that both of these are undefined. If theta is coterminal with any angle on the x-axis. So both of those are undefined if theta is coterminal with 90 degrees or pi over 2 radians, if you're going to use radians, or 270 degrees or 3 pi over 2 radians. So any angle that's coterminal with those, these are both undefined. So if I was going to make this initial table, you can't calculate x and y at pi over 2 or 3 pi over 2. You can advance through there otherwise, but it's undefined at those points. So let's say I just started here. You know, how do you advance from pi over 2 to 3 pi over 2? You would do pi over 2, 3 pi over, so that's 90, that's 135, that's 180, that's 225, that's 270. And if you just did the math up there, you get that and that and that, and you're going to see your points advance from here, negative 8 root 2, negative 7, to here, negative 8, 0, to here, negative 8 root 2, 7. So like in that direction. In this table, advancing the angle or theta from pi over 2 to 3 pi over 2, those are the points I can plot out. Okay, it's getting me that part of the hyperbola. Remember, this is a hyperbola. It's got two distinct separate pieces. Now, there's more angles, though. What about the angles in quadrant 1 or 4? Like, so say, how could you advance from negative pi over 2 to pi over 2? All right, so I'm thinking like pi over 2 to 3 pi over 2. That's this table. And then this table, negative pi over 2, so that'd be like if I rotate it down there, up to pi over 2. So that'll cover the rest of it. These two tables cover everything, all four quadrants. Okay, what about this one? Negative pi over 2, undefined. Negative pi over 4, 8 root 2, negative 7. Oh, so that's this point right here. 0, 8 and 0. Theta pi over 4, this point right here, 8 root 2, 7. So like that direction. As theta advances, your points are tracing this way. Now, one more thing about the nature of the graph is like, can you kind of run, you can't have pi over 2 negative, and you can't have pi over 2 positive. Can you run up against them? All right? You can't have pi over 2 and you can't have 3 pi over 2. Can you run up against them? Now, for this, we have to do a little bit of reviewing in pre-calculus about how you calculate secant and tangent. But if you push to pi over 2 from below, like what happens like right here? Then, by nature of secant and tangent, x and y will both go to infinity. Oh, so it's like it'll follow that curve out to forever. In this way, out there, that part of it. And what if theta goes to negative pi over 2 from below, all right? Like say, or from above, sorry. I don't know, like from right here, what happens right there? All right, well, okay, so if you do that, still, just by knowing about tangent and secant, how they're calculated, when you learn pre-calculus, then x will go to infinity, and y will go to negative infinity. Theta goes to negative pi over 2 from above. Those are the limits. So that's like this part of the curve. X going out to infinity, y going to negative infinity. You'll get the whole curve. So if you could fill in like, if you could like push to where it's undefined from each side, you'd like get the rest of that curve out to forever, out to infinity and negative infinity. And on this one, if you did the same thing, you push out here, you push to the undefined, then it'll get you the rest of it, get you the whole thing, okay? So those, given that you restrict where it's undefined, will get me this every single point on that hyperbola, all right? Okay, so that's the most complicated one. If you're unsure of the limits, we can talk about that. It only takes a little reviewing about how secant and tangent are calculated. But I think that is an important part of extrapolating from these tables a little bit and seeing that we get all of it. We get the entire graph.